Alright guys, so we're going to look at optimization problems here. As always, I'll start with the bell work, which kind of reviews previous things or things we need to know. And so if you haven't done them, pause it. Otherwise, stay tuned. So we've already done dy dx. We haven't talked a lot about it, but basically this means that we're going to take the derivative with respect to x, which means that this here is just going to be y prime like we've done before. And then over here, this is going to be a chain rule. So it's going to be 5 times the cosine of 2x to the power of 3. And then we got to multiply by the derivative of the inside, which is 6x squared. Or, more simply put, 30x squared cosine of 2x cubed. Now for this one, it's not really any different, except that this time it's telling us, hey, we're going to take the derivative with respect to r. Meaning that if there's an r, that's the thing we're deriving. So in this case, it's just a prime equals 2 pi, because the r would become 1. And then likewise down here, we're taking the derivative this time with respect to t. The one on the bottom is the one we're always taking it with respect to. So we're going to start by taking the derivative of this thing. Before I do that, I'm going to rewrite it because it's a whole lot easier for us to do it if it's written this way, or it's a little easier to comprehend. So that's going to be that r prime is equal to negative 12 t to the negative 2, or really negative 12 over t squared. Then at that point, it tells us find it when t equals 3. So that means that we're going to find the rate that the radius is changing with respect to t, probably time, when time is 3. So we're going to get negative 12 over 3 squared, which is negative 12 over 9, or more simply, negative 4/3. All right, let's put this into some practice when we're doing some bigger problems here. So these are just some rules, not rules, guidelines, ways that are good to solve these things. So you draw a diagram if you can, or if you need to. Find the thing you want to maximize or minimize, and that means that you need to find a formula that's going to work out those variables. It uses all the variables you have. And then you're going to solve for your max or min. Okay. Now checking the endpoints, that's not really as important to what we're doing right now. We will kind of do that in the future, but for now, we're not going to really look at that. So if we look at this first one, the surface area, a centimeters squared of an expanding sphere of radius r centimeters, is given by this formula. And so then what we need to do is find the rate of change for the area with respect to the radius. So in other words, we need to find dA dr. Okay. So if we start with our formula here, then we would take the derivative, which will give us 8 pi r, because we're just taking the derivative with respect to r there. And then we want to do it specifically at r equals 6, because we want to do it at the instant that the radius is 6 centimeters. So that means that our area is going to be expanding at 8 pi times 6, or more simply put, 48 pi centimeters squared. All right, so that's how this is going to be. That's like what's going on at the exact moment that the radius is 6. Okay. Now, if we're looking down here, we've got a large tank with the shape of a cuboid, and it's to be made with a certain amount of sheet metal. The tank has a horizontal base and no top. The height of the tank is x meters. The two vertical faces are squares. So what this means is, first of all, let's draw a picture. This one's a little bit trickier. So we've got like this rectangular prism here, where our ends are squares. So that would be like this one here and this one. And so they are of height and length, or width and height, however you want, of x. And then we've got y to represent our other variable. So what we're going to do here is we need to figure out like how to get rid of one of these variables, because currently we have too many. So we want to show that the volume is equal to this. So we're obviously going to need our volume, and our volume is going to be y times x, or x squared y, more simply put. But as you can see here, we have too many variables, so we need to get rid of one. That's where this 54 meters squared of sheet metal is going to come in, because of course that's an area, and so we can use that to figure out what our area of this thing. Remember, there's no top, so that means we've got these two sides that are xy, or sorry, x squared, and we'd have the front, back, and bottom, or 3, that are xy. We also know that the area is 54 meters squared because it tells us that we're going to use that much sheet metal to make this box. So then what we can do is we can take this and solve for y so we can plug it in. So we're going to get 54 minus 2x squared divided by 3x is equal to y. If you're having some trouble with the algebra, pause it, review it, right? But this is stuff we've done before, so we don't need to really go over it. Then what we're going to do is we're going to take that and plug it in for y. Because ultimately, this, right, is y, so I can just replace that y there with it. So now my volume is going to be x squared times 54 minus 2x squared over 3x. Now, personally, I think it's going to be simplest if we remove one of these common factors right away and get rid of that x and just multiply an x in. So then I'm going to get 54x over 3 minus 2x cubed over 3. Now I can simplify that a little bit more there, and I'm going to get, what is that going to be? 18x minus 2x cubed over 3. And so we have now checked off A. We've done exactly what it told us to. Then we want to find out what x we can use in order to find a maximum or minimum for this thing. So what that means is that we need to take this and we're going to need to differentiate it now, because we know that when we differentiate, we can find our max or mins when they're equal to 0. So that's what we're going to do. So we differentiate this. We're going to get v prime is equal to 18 minus 2x squared, because the 3 comes down and cancels with that 3 underneath. Then what we need to do is set this equal to 0 such that we can solve for what x should be. So we'll get 2x squared equals 18, or x squared equals 9. I'm going to bring that up here, which of course means that we can take the square root, and x is going to be equal to technically plus or minus 3, but obviously having this side length here be negative 3 makes no sense, so we're just going to use x equals 3 because having a negative sign length doesn't make sense. All right, now justify that the value we found is indeed a maximum. So you'll remember that when we're doing this, I guess I should put that this was B here. That was part A. And part C is to prove that it's a max. So remember, this is where we did a sign analysis. So we plugged in values that were on either side of our critical point here, and we're plugging them into the derivative. So for this part, I'm going to use this one right here. And all I'm really trying to do is figure out the sign, right? I want to know what's going on with it. So when I plug in 2, I get 18 minus 2 times 2 squared, which is 8. So it's going to remain positive, which means it's increasing, right? The original function is increasing. When I plug in 4, though, I'm going to get 16 times 2. That's 32, which is more than 18. So that's going to be negative. And so that means it's decreasing. And so that, of course, proves that this is indeed a maximum. All right. Perfect. Let's look at some more examples of how this can work. So let's change up our shape a little bit here. This time we're going to look at a cylinder. We've got a surface area again, so we're going to need that surface area equation. And we've got to find the volume. So that means that we're going to have to use both of those. So our volume is pi r squared h. Okay, and of course the issue here is that we have two variables, r and h. We need to get rid of those. So let's go ahead and do the area then. Area of a cylinder, it's closed, so it's got a top and bottom, is going to be 2 pi r squared for that top and bottom, plus 2 pi r h, which gives us the rectangle part, like the soup can label, if you want to think of it that way. So what I need to do now is plug in what I know and solve for h so that I can get rid of it. So first thing I'm going to do here is I'm going to move that over, so 600 pi minus 2 pi r squared, and then I would divide by what's left, which is 2 pi r. Now this is helpful because there's a whole lot of simplifications we can do. Obviously there's a pi everywhere, and there's a 2 everywhere, so I can also get rid of that. And so now I've got 300, I should say 300 over r, minus r squared over r is just r. So I can have it like this, be equal to h, and then I can go ahead and I can plug that in order to figure out what my new volume is. So this volume is going to be pi r squared times 300 minus r. Oops, not all over r, just this one. And then I'm going to simplify that to put that in, to distribute it. So I'll get 300 pi r squared over r is just r, and then pi r cubed, like so. So at that point, we have shown that that is exactly what we wanted the volume to be. So then we can go ahead and start finding that maximum. So what we're going to do is take the derivative, which is going to be 300 pi minus 3 pi r squared. Then we know that whenever I'm finding a critical point, I make it equal to 0. And so then I'm going to move this over. Then I can divide. And so I'll get that r squared is equal to 100. And let's just bring that up here for a second. There, rather. R squared equals 100. We can square root that to tell us that r is actually 10. Now, technically it's plus or minus 10, but same as before. A negative distance here for the radius makes no sense. And so this would be our answer. Okay, but this one does say find the maximum volume. So if we want to find the maximum volume, we need to actually put that value in there. So I would recommend using our simplified version right here. That's the one we're going to use. And so that's 300 pi times 10 minus pi times 10 cubed, which this here is going to give us 3,000 pi. 10 cubed is 1,000, so 1,000 pi. So our final answer will be 2,000 pi, and we don't have, oh, we do have a unit. There we go, centimeters. So centimeters cubed. And that would be our final or maximum volume that we could get. We cannot get one bigger. All right. Now let's take a look at something a little bit different here. We're going to do something where instead of using surface area and volume, we're going to look at something that deals with perimeter. So in this case, we've got a rectangular field, and one side is against a stream, so it doesn't need any fencing. So we got like this stream here, okay? And then we need to have a rectangular field like this, which is probably easiest to just represent with our two variables. And our surface area, or our area really, is going to be x times y, right? That would be how we'd find that. We're assuming the river is roughly straight. And then our perimeter is going to be 2x, because this would also be x, plus y. But we know that that total perimeter is 1,400, because that's how much fencing we have or can afford or whatever it is. And so then, just like before, we're going to take this, we're going to substitute, or not substitute, we're going to solve for y, so that then we can take that and plug it into our area formula. So our area is going to be x times 1,400 minus 2x. I always like to simplify those. So that's going to give us 1,400x minus 2x squared. Now, obviously, we don't have to. We could later take the derivative of this with it being a product rule, but why? It's so much easier to just plug this x in. And as we learned earlier, it's much easier to take the derivative of a polynomial-like looking function. All right, so now we need to know what are the dimensions. Well, that means that we need to figure out what is going to maximize x here. So we're going to have to find a prime, which will be 1,400 minus 4x. Then we make that equal to 0, because we know that that's going to be our critical points. So 4x equals 1,400. And then we can divide by 4 to get that our x should be 350. So that's great. We still need to find y, though. The easiest way to do that is to take our perimeter equation there. So 1,400 equals 2 times 350, because that's our x, plus y. And so 1,400 equals 700 plus y, or 700 equals y. Sorry, I should say 700 meters. So that would be our two dimensions. Or more specifically, we could say that it's going to be 350 meters by 700 meters would be our answer. Awesome. All right, couple more examples. No, actually, sorry, that's it. We're done. So after that, guys, you can go ahead, take a look at the practice problems. And of course, I'll post up the answer key as well for you to take a look at.